Okay, so we just discussed the Gram-Schmidt algorithm, and the Gram-Schmidt algorithm is great because it produces QR factorizations, but it's certainly a little bit tedious to run through because there's all these projection vectors we have to calculate by hand. This is the kind of thing that you should try a few times by hand, but once you get the gist of it, you should just ask a computer how to do all of it. So I want to run through a few pieces of code that I've written that I hope will help. So in the first box here, this will calculate the projection of any vector v in the direction of another vector v1. This is the projection formula in one dimension, and we called this proj sub v1 of v in the lecture for Gram-Schmidt. So all we have to do is we input the vector v1 here, and then we input the vector v. The vectors I've input are in R4, and so if we click evaluate, on the first line, we'll print out v1 just to make sure we input it correctly. On the second line, we'll print out v, again, just to make sure we've input it correctly. And then in the third line here, this gives us the projection of v in the direction of v1. And it's this kind of nasty vector we see over here. In the second box, we can calculate the component of a vector v in the direction of another vector v1. The formula for this is the inner product of v1 with v divided by the length of v1. Again, this is an easy definition, but it can be a little bit annoying to do by hand. So this piece of code will do it for us. All we have to input is the vector v1 and the vector v. And so I've predefined v1 and v as these two vectors in R4. If we click evaluate, v1 and v will print out again so we can check that we input our data correctly. And then this will give us the component of v in the direction of v1. Here we see that component is the scalar given by negative 35 over 57 times the square root of 114. Remember, the fact that this scalar is negative tells us that when we project v onto v1, we'll get a vector that points in the exact opposite direction of v1. And finally, and most importantly for us, the Gram-Schmidt algorithm or I guess this isn't finally, we'll do one more thing, but importantly for us, we can apply the Gram-Schmidt algorithm with Sage, and this is nice. So remember, the Gram-Schmidt algorithm takes as an input any basis for a vector space, and then produces two new bases. The first basis, which we label with W's, is a mutually orthogonal basis for the space. And then the second new basis is labeled by Q's, and that's an orthonormal basis for the space. Applying Gram-Schmidt is a bit tedious, especially if you have a lot of basis vectors, because you have to subtract off all of these vector projections at each stage. And so the numbers here can get a bit ugly. So it's nice that Sage can do this for us. So the Gram-Schmidt algorithm is actually built into Sage. So here, all you have to input on the first line is a basis of the vector space you care about. So evidently the space I care about is dimension 3 because I've predefined 3 basis vectors. And so if we click evaluate, let's see what happens. So here, the first thing that's output is the basis that we've input, so we can check that we've input our data correctly. So here I have my 3 vectors in R4. And then the next line will give us the mutually orthogonal basis of the space. These are the W's that pop out of the algorithm. So here I get 0, -1, 1, -1, 1, 0, 0, 0, and 0, 2, -1, -3. So those are the W's. And then to finish the Gram-Schmidt algorithm, we have to normalize all of those W's. And that's what's printed out in the third line here. So these are the Q's. So here we see the normalization of 0, -1, 1, -1 is 0, -1/3 times root 3, 1/3 times root 3, -1/3 times root 3. And then the same goes for the other two basis vectors. We normalize the last two W's to get the last two Q's. So if you're working a Gram-Schmidt problem by hand, you should certainly use this as a tool to check your work. And finally, one of the reasons the Gram-Schmidt algorithm is so powerful is that it gives us QR factorizations. So remember, to get a QR factorization, you apply Gram-Schmidt to the pivot columns of your matrix A, and then put the orthonormal basis that pops out of that algorithm into the columns of Q, And then you can define R to be Q transpose times A. So here I have, I'm defining our matrix A on the first line. And if I click evaluate, this will use Gram-Schmidt to give us a QR factorization. So here A is this 4x3 matrix. And then I've used the Gram-Schmidt algorithm to factor A as Q times R here. This is the same example from the end of the lesson. So you can use this calculation to check that I said everything correct in the lesson. So if you have A and you want Q times R, this code should help.